Good, Simitinan. Okay, I think you are all ready for the weekend. I'm also ready for the weekend, but first of all, we have to finish with the GPU. Yesterday, we finished with SIMD processors, and we took a look at the GPU architecture. Today, we're going to focus on GPU programming. We will also review the GPU architecture because it's going to be very important, especially for the performance considerations, that we keep the architecture in mind when we want to program and we want to efficiently program the GPU. But now we will be more focused on the programming model and on the programming language that we typically use to program GPUs for general purpose, because I'm not going to talk about programming GPUs for graphics. So this is the agenda for today. We are going to talk about the GPU as an accelerator. So in those systems that we are going to use GPUs for general purpose processing, we will still have a CPU that will be like the ruler, like the one who is going to lead the computation. And from time to time, the CPU will offload some of this computation to the GPU because we will know, or the CPU will know, that this computation is going to be more efficiently executed on the GPU. We will talk about the program structure, so how these programs with CPUs and GPU are structured. We will talk about the memory hierarchy, what to do with memory in order to have an efficient access to it, because as you can, we will talk about that. This is one of the main bottlenecks still in GPUs. And finally, we will go through some other performance considerations, like how to improve the SIMD utilization in these GPUs, or other important things like the use of atomic operations or the data transfers. So we don't have required readings for this lecture, but there are some recommended readings, especially if you, after this introduction to GPU programming, want to learn more. I strongly recommend you to read the CUDA programming guide and also this book, Programming Massively Parallel Processors, by Professor Hu and David Kirk, who is a chief scientist in NVIDIA. First of all, let's finish with the slides that we had yesterday. These slides are simply like taking a look at a real GPU, okay? So that's why this is an example GPU, and this example GPU is an old one. It was one of the first that was used for general purpose computing. It's a GTX, or NVIDIA GeForce GTX 285. As you see, in NVIDIA terminology, it has 240 stream processors. What are these stream processors? So this is what we call the vector lanes. So this GPU had, or has, 240 vector lanes. These are arranged, recall that the vector lanes are arranged into SIMD cores or SIMD pipelines. So in total, this GPU has 30 SIMD pipelines, each of which has 8 lanes. So 8 SIMD functional units in each of these cores. If we take a look at one of these cores, this is, by the way, this SIMD pipeline or SIMD core has, in NVIDIA terminology, is called a streaming multiprocessor, or SM. Where you're going to see it several times through this presentation. And what do we have within each of these SMs? We have decode logic. We have some registers here, some thread context, essentially the registers that, as you know, are partitioned for all the vector lanes, for all the threads that we are going to execute here. And then we have our functional units. As you see, there are 8 functional units in each of these SMs, in each of these cores. So how are these used? Well, in each of these cores, we are going to have a certain number of warps. Recall the warps, that is a collection of 32 threads that are executed in each of these SMs. So, and as you might remember, in the GPU, we use fine-grained multithreading. So these warps are interleaved. We first launch instruction 04 warp 0, then we launch instruction 04 warp 1, and then maybe we launch instruction 3 for warp 4. So because there are only 8 functional units here, the 32 threads will be executed in 4 cycles. This is something that, let's say, we are reviewing from yesterday's lecture. This is the complete, this is the complete GeForce GTX 285. You can count the number of SMs. There are 30 of these SMs or cores. And even though this looks kind of impressive, right? There are a lot of computing power here. This is nothing compared to the evolution in the recent years. Look, this is where we have, where is my pointer? This is where we have 285 that was launched in 2009. It had 240, one of these stream processors that are our vector lanes. And if you look at the right axis, this is around 700 gigaflops. You can compare with the NVIDIA GPUs that have been released in later years, and the most recent one is this V100 that was released last year, reaching up to 15 teraflops. So it's around 20 times faster than the one that was released in 2009. So you see how this has been improved and how the hardware has been optimized in recent years. And this is the NVIDIA V100. In total, it has 80 cores or SIMD pipelines, and in each of these, we have 64 functional units. Let's take a look at the entire block diagram of the V100. You can count there are 80 of these SMs or SIMD pipelines, and if we take a closer look at each of them, this is one SM, and as you can see, it's actually divided into 4 parts for different reasons that we exactly don't know, but maybe we could try to figure out. But the thing is that you see they are organized in 4 of these parts, and if you look at this, you see that there is one instruction cache where we are going to store the instructions, and we're going to fetch the instructions from them. Then we have the warp scheduler, which is the unit that makes the decision of when launching or issuing an instruction, a specific instruction for a specific warp. So it's the one that selects the warp to execute. Then here we have the register file, and here several specialized units, specialized or functional units for different purposes. For example, there are some of them here specialized for double precision floating point operations. Then we have integer floating point units. And then we also have these so-called tensor cores that actually are kind of specialized functional unit for machine learning. You know that machine learning and deep learning in particular is more and more used in current applications in many different fields nowadays. So that's why they decided to include these functional units. You can take a closer look at this. This is essentially, it's intended to do matrix multiplication. That is an essential operation in current deep learning applications. You can take a closer look here and maybe find more information in this link. So after taking a look at the most recent architecture of NVIDIA GPU, now let's start talking about how to program this. And you might remember this slide from last week. The disadvantages of vector processor. Remember this paper by Fisher that said the compiler or a hand coder must make the data structure in code fit nearly exactly the regular structure built into the hardware. That's hard to do in first place, and just as hard to change. So what Fisher tried to explain here was how difficult it was to program SIMD processors. Luckily, with the SPMD, with the single program multiple data programming paradigm that we introduced yesterday, now it is much easier to program these SIMD processors that nowadays are called GPUs. This is the main reason probably why we can say that the GPUs have democratized high-performance computing, because now the amount of computing power that they have, it's, let's say, accessible to many more programmers and many more developers. And actually, that is something good, because there are many different workloads that exhibit inherent parallelism, many different workloads in which we can process many data instances at the same time. Good examples are matrices, as I just mentioned, for deep learning, or image processing. Actually, throughout this presentation, we will talk about these two as examples. However, this is not for free, and that's why we are talking today about this, because it's necessary to learn a new programming paradigm. It's necessary to get used to parallel programming, to the fact that now you're going to have many threads computing at the same time, and you might need to keep in mind how these workers need to, at some point, synchronize, or need, at some point, have to share data among them. But that's why I think that this lecture today might be interesting for you. You are now starting in this first year to get familiar with computing systems. Probably some of you are already have some knowledge about parallel programming. If not, this can be a good starting point. And probably in later courses, you will learn much more. So, but even though GPUs are great, and now it's super easy to program them, there are still some bottlenecks, and we also have to learn how to deal with them. One of the main bottlenecks is the fact that we still need to move data, a lot of data movement from the CPU to the GPU. As I said in the beginning, the CPU is still like conducting the execution. It's like the ruler, right? So at the very beginning, we are going to have data in the CPU memory. But if we want to offload something to the GPU, to do the GPU something for the CPU, we will have to move data from the CPU memory to the GPU memory. And when the GPU finishes the computation, we will have to move back the results from the GPU memory to the CPU memory. And as you will see, this time is not negligible. Usually it's not negligible. But we will also, at least we will try to reach to that point in which we discuss a little bit how we can also try to deal with this. And the other main bottleneck is the access to the memory bandwidth. If you go to the NVIDIA GPU specification and compare to one CPU specification, you will see that the bandwidth, the theoretical maximum bandwidth of NVIDIA GPUs is much higher. But still, it's going to be a problem, because instead of having 1, 2, 4, 8 cores, as we have in CPUs, now we have thousands of threads that are requesting data from this memory. So still, we are going to see that our applications will tend to be memory bounded. So always it's good to do a good use of this memory bandwidth. Let's take a quick look at the, maybe you are, I mean, you are already familiar, let's say, with this distinction between CPU and GPUs, but let's quickly recall it, right? What is a CPU? A CPU typically has only a few out-of-order cores. In GPUs, we have many in-order, fine-grained, multi-threaded cores. In the CPU, as you can see, most of the chip area is devoted to control and is devoted to large caches. In the GPU, on the other hand, what we have is many in-order cores. So most of the die area is devoted to these functional units. Okay, as I mentioned, as I have already explained, we are going to offload the computation to the GPU, and this has 3 steps. In the first step, we move the input data from the CPU memory to the GPU memory. Then we launch the kernel. We call kernel like the function that is going to be executed on the GPU. GPU function and kernel is the same. And we will have our threads running in these GPU cores and doing something with this input matrix. And we produce some result, maybe some output matrix that finally has to be transferred from the GPU memory to the CPU memory. So let's start taking a look at CUDA code, at the programming language itself. You will see that it is very similar to C. We can say that it's kind of C with some extensions. Yeah, but first of all, let's see what's the general program structure that we are going to have, because still, as I said, we have CPU and we have GPU in our system, and probably we will have to use both, depending on what we want to compute. In the beginning, I mentioned there are many workloads that are inherently parallel, and we want to exploit this parallelism on the GPU, but there are still many other workloads or several other workloads that are not parallelizable, or they are only modestly parallel. So that's why we will run the modestly parallel or sequential sections of our code on the CPU, the massively parallel sections on the GPU. So our code is going to look something like this. We will have one CPU thread running some serial code. At some point, we reach some computation that is parallel, and we offload it to the GPU. Then the control returns back to the CPU that maybe has to execute a few more instructions with one or maybe two or four single threads, and finally, or in this particular example, another kernel. One interesting thing that you can already observe here is that in the GPU, we're going to use many, many threads, thousands or millions of threads. But these threads are arranged so that the entire collection of threads is called a grid. And within this grid, we are going to distribute, we are going to organize the threads into blocks. So we are going to talk about a grid of blocks of threads. And when we call our kernel or GPU function, we will launch a certain number of blocks, each of them containing a certain number of threads. We will repeat this, don't worry about that. So you already know this slide as well. We used this slide yesterday. It's like the introduction to the single program, multiple data programming model. Remember, that is a programming model more than a computer organization that allows us to execute parallel programs and write them in an easy way and execute them on SIMD processors. Also recall this, these procedures or these threads of execution can synchronize at certain points in program. We are going to talk about that. They work on different data, and they can execute a different control flow path. We yesterday already talked about what were the implications of branch divergence, right? Now we are going to deal with this again from a software point of view. So let's start with this SPMD or SIMT programming model that is the programming model for NVIDIA GPUs, but not only NVIDIA GPUs, also AMD GPUs. In NVIDIA, we typically use CUDA programming language, but there is like a more cross-platform programming language that is OpenCL that can be, let's say, it's cross-platform because we can use it on NVIDIA, on AMD, on Intel, and not only on GPUs, but also on CPUs. All the concepts that I'm going to introduce in this lecture apply to both CUDA and OpenCL. The only difference is some different names for some of the concepts, but I will point out these differences, but essentially the programming model is the same. And both, we say that they are bulk synchronous programming models. Why are they bulk synchronous? Because we can only synchronize at certain points, as remember the previous slide said. So what are these certain points? Are between kernels. Recall the 2 slides ago where we had the CPU thread, then kernel A, then another CPU thread, and then kernel B. The only way to make sure that all these threads in kernel A can synchronize is when the kernel terminates. So this is the only point between 2 kernels in which we are sure that the computation of all these threads running in kernel A actually finished. Let's say that, I mean, this is why this is called bulk synchronous programming model. The host, as I said, the CPU, now we're going to talk about host, is going to be typically a CPU, is going to be in charge of allocating memory, not only in the CPU memory, but also in the GPU memory. It will be the one who will take care of the data transfers to order the data transfer from the CPU memory to the GPU memory. It will launch the kernel, and it will also take care of the data transfer from the GPU memory to the CPU memory. The device, that is a GPU, executes the kernels. And as I have mentioned in the previous slide, these kernels, the threads in these kernels, are organized into a grid. This grid is divided into blocks, and in each block we have threads. In the brackets, what you see is the same thing with the OpenCL terminology. It's interesting, even though this is bulk synchronous, and the only way we can synchronize all the threads is between kernels, within a block, it's also going to be possible to synchronize. We're going to have like kind of local barriers or local synchronization points. We will talk about this. By the way, why is it useful to divide the computation, divide the entire grid into thread blocks? Why is it useful? Because it allows something that is called the transparent scalability. I mean, if you write a parallel code and you want to run it on the multi-core, probably what you will have to do is say, okay, how many cores do I have in this CPU? Do I have 2 cores? Okay, I'm going to launch 2 threads. But if I have 4 cores, probably I will launch 4 threads, and if I have 8 cores, I will launch 8 threads, right? So I will adapt the parallelism in my code to the hardware that I have, or someone will do that for me, maybe the compiler, maybe the runtime. In the case of the GPU, there are also different GPUs with different architectures, with few cores, few SIMD pipelines, or many more. And I want to run the same code. I don't want to change my code every time I change the GPU. So that's why if I define a kernel grid in which, for example, I have 8 blocks, I want this code to be compatible with every GPU, at least from the same vendor, right? From NVIDIA, for example. So what I will do is scheduling the thread blocks in a way that will depend on what's the underlying hardware, what are the specific number of cores that I have in my hardware. So for example, let's consider that our device has only 2 cores. So how are we going to schedule these 8 blocks here? For now, we can assume that each SIMD core is going to execute 1 thread block. So we will do something like this. I mean, not us, some hardware that is called the block scheduler that takes care of this. We'll go through our program. We'll say, okay, my programmer wants to launch 8 blocks. Now I'm going to schedule these 8 blocks in these 2 SMs, in these 2 SIMD cores that I have here. And this is one possible order of execution. First of all, block 0 and 1. When these 2 finish, block 2 and 3, and so on. And actually, if one of these takes more time than other, let's say that block 1 takes longer to finish than block 0, as soon as block 0 finishes, it can be replaced by another block. Another important thing, I cannot be completely sure that these blocks are going to be scheduled in a round robin. I cannot be completely sure that block 2 is going to be executed after block 0 or block 1. There's no guarantee about that. The only way that makes sure that block 0 terminated is waiting until all thread blocks terminated. If I have 4 cores, I will schedule something like this. Okay? Any questions so far? Okay, now let's start taking a look at the memory hierarchy. Remember that we have a grid. Within this grid, we have many threads, and they are organized into thread blocks. Okay, what's the different memories that these guys can access? They all will have access to the device memory, this dark orange thing that you see here, even though it's divided into 2 parts. There is some part that is used for constant operands, but you don't have to worry about that now. Just simply consider that all these dark orange thing is the GPU memory, and we are going to talk about it as global memory. So all threads, no matter to what block they belong, can access this global memory. But also observe that those threads, like these two, 0, 0, and 1, 0, that belong to the same block, have access to the same shared memory. So in each of the streaming multiprocessors, we have one on-chip memory that is really fast, much faster than the global memory, where the threads running on this core can store intermediate results. So that's the shared memory. And as you can see, threads belonging to the same block can share data through this shared memory. And they also will make use of their own registers that are private. This is you remember from yesterday's lecture, the partition register file. So that's what we have here. Okay, let's start reading some CUDA code. There are some function prototypes. You're already familiar with this. This is a function prototype in C. This is a function prototype in CUDA. This is a kernel. It's essentially the same thing, but in order for the compiler to distinguish these two, we have this global qualifier. So in our declaration, we will use this global, and also in our definition. In our program, we will have main. This is the main function in our C program, and that is going to be run by the host, by the CPU. And the first thing that the host will have to do, besides allocating memory in its own memory, in the main memory of the CPU, it will have to allocate memory on the device using something very similar to malloc. This is called CUDA malloc, right? Then, at some point, we will need to transfer data from CPU to GPU. We use CUDA memcopy, and then we have to decide what's the execution configuration. When we talk about the execution configuration, we talk about the number of threads per block and the total number of blocks in the grid. And then we call the kernel, and when the kernel finishes, we will retrieve the results from the CPU, from the GPU memory to the CPU memory. Observe here, this is like a good convention, right? This is the destination in this memcopy. D means device, H means host. So we are copying from the host to the device. Here, we are copying from the device to the host. We can repeat this as many times as needed. I mean, in many iterative algorithms, we will have to repeat this many times. Or maybe it's not an iterative algorithm. It's simply that we have written a second kernel or a third kernel that maybe implements another stage of our application. So these steps will be repeated over the entire execution of the application. Yeah, just to recall the global void kernel in this case. So we have seen the previous slide, like the memory hierarchy, right? We have registers, we have shared memory, we have global memory. These guys here, this D in or this D out, are going to be stored, are allocated in global memory. But then we can allocate something within the kernel, within the function kernel. We can declare some shared memory arrays that are useful for the thread blocks and for the threads in these blocks to move probably some data from the global memory to the shared memory that is kind of software managed cache. We will talk about that later. And also, just for you to start getting familiar with this, we have this intra-block synchronization, this local barrier that I mentioned before, is these sync threads. For you to know the exact syntax of all these operations, here you have the syntax for CUDA malloc. This is the in is a pointer to some specific memory space, the number of bytes that I want to allocate. This is a memory copy, destination, so D in is the destination, H in is the source, the number of bytes that we're copying, and actually observe there from host to the device. Obviously, we also have like the a specific word from the device to the host. Then this is the syntax of the kernel launch to deallocate memory on the GPU. And this is just like the explicit synchronization. Just in case we want, for example, if we want to measure the execution time for a kernel, you put a timestamp in your CPU code, you put a timestamp here, then you launch the kernel, and then another timestamp here. So if you want to make sure that the kernel has finished, you will have to use this CUDA device synchronize. It's one of the possible uses of this CUDA device synchronize. Okay. Remember yesterday, one of the last slides was, okay, now I have in my GPU thousands of threads. They are going to operate on many different pixels or matrix elements. How do we access them? How do we tell each specific thread you have to work with this pixel? So this is what we are going to talk about. As I said in the beginning, one of our running examples here are images because they have a lot of inherent parallelism. They are, as you know, images are two-dimensional data structures. They have certain height and certain width. In this example, this is a 8 × 8, very simple image. And the way in C code that we want to access any of these elements is making use of the row and the column where one specific pixel is stored, right? So, for example, here, image JI will be one of these pixels where J is between 0 and height and I is between 0 and width. So, for example, this is image 01 and this is image 12. This is easy, right? So now let's see how threads in the GPU are going to access this. We assume, and not only assume, in CUDA C, we use a row major layouts that we explained yesterday, as you might remember. So in this row major layout, if we want to access image JI, what we are actually doing is accessing memory position J times width, which is the number of columns, plus I. So this is my image, and this is how my image looks in the GPU memory. And this stride is the width of the image. So this is row 0, row 1 is somewhere here, row 2 is somewhere here, and so on. So my element 01 is actually in this position that is image times 8 for this specific image plus 1. And this element here is image 12 is in image 10. Actually, it's in the image 1 times 8 plus 2. So now we are going to see how assign these image pixels to the GPU threads. Initially, we are going to assume like a naive or straightforward mapping, right? In which each of the pixels is going to be assigned to one thread of execution. Remember our grid of blocks of threads, and this is CUDA. I mean, this is like the built-in variables that we use in our programs to identify or define the dimension of the grid. Observe that we talk here about a one-dimensional grid. So all our threads are arranged in a one-dimensional organization. And this grid is one-dimensional, so grid dim represents the total number of blocks in this one-dimensional grid. And block dim is the total number of threads in each of these blocks. What's the total number of threads in the entire GPU? Is grid dim X times block dim X. And now we want to identify each of these blocks, and I want to identify each of these threads in each block. So for that reason, we need to use this block index.x and thread index.x. Let's see how to assign the different pixels of the image to blocks and threads. For now, we are going to assume that our blocks are very small. You remember from yesterday's lecture that in the beginning of today's lecture that warps contain 32 threads, right? That's the minimum block size that we are going to use. But for this toy example, let's consider that the entire block has only 4 threads. So what we will do is assigning these 4 pixels here to block 0. And what we do is distributing all these pixels among all the available thread blocks that we are going to launch. And if we take a closer look at block 0, what we will do is assigning this pixel to thread 0, this pixel to thread 1, this pixel to thread 2, and so on. And each of the threads will run some simple or complex computation on each of these pixels. I don't know, maybe changing the exact color a little bit, adding some brightness or reducing the brightness or something similar. So let's see how these threads that now we have, like, for example, this thread 1 in block 0 is going to identify its own pixel. We need to use block index and we need to use thread index. So if in this simple mapping, we are assigning threads in some consecutive way. So what we are going to use here is like what we call a global thread index. Observe that this one particular thread in block index X with thread index X will be, in the whole GPU, will be blocks idx.x times block dim.x, which is a total number of threads per block, plus the index in the own thread block. So for example, this pixel here is going to be assigned to global thread ID 25. If you count the thread block, this is block 0, block 1, block 2, 3, 4, 5, 6. So block ID x.x is equal 6 times 4, which is the total number of threads in the block, plus 1, because within this thread block, this is thread 0 is going to work here, and thread 1 is going to work here. So this is a way, using this global index, that threads are going to know, okay, I have to work with this specific thread, this specific pixel. I will have to access it in memory, compute something, and maybe write it in a different or maybe the same memory location. Grids are not only one-dimensional, they can also be two-dimensional or three-dimensional. Here you can see an example of two-dimensional grid with two-dimensional blocks. I will let you think about this yourselves. But as you can see now, and probably this is usually a better organization for images, because images are two-dimensional, so probably it makes more sense to use. That also depends on the programmer. The performance might not have many differences. So what we could do here is dividing the image into chunks or blocks. I mean, actually, we will talk about this. This is called tiles. And each of these tiles of the image is assigned to one thread block. So for example, this here is assigned to block 0, 0. And now this guy here is going to be, so it's going to have like two indices, block index X and block index Y. So for example, this tile here is assigned to one thread block that is X equal to Y equal 1. And in the same way, we have two IDs for the thread. In this case, the one there is thread index X equal 1, thread index Y equal 0. And if we want to tell each of these threads, hey, you have to access this specific pixel here, what we are going to do is, for example, computing the exact row and the exact column in which the pixel is stored. So observe that here we are using block index Y, block dimension Y, and thread index Y to calculate the row. I will let you think about this. It's a very easy calculation, and you will quickly understand. Okay, before we continue with programming language, let's take a quick review of the GPU architecture. We are already familiar with this, but I just want to make sure that you all recall. I mean, you already saw that the entire GPU is divided into SIMD cores that NVIDIA, for example, calls streaming multiprocessors. That's like in this old architecture, the G80, GT200, to which the GTX 285 belong to. We have something called the streaming processor array, and within this streaming processor array, what we have are all these streaming multiprocessors. Remember that we have an instruction cache, we have some unit that decodes and issues the instructions on top of these vector lanes that are called SPs here. We will see in the next slide what the meaning of this. Here we have the register file, and also remember the shared memory. This is a newer generation. It's also quite old. This one is NVIDIA Fermi architecture, was released in 2010. And as you can see now, it's a little bit more complex. Instead of having these 8 of these SP, which are the vector lanes, now we have 32 lanes. And now, actually, interesting, we have 2 warp schedulers. So it's like having 2 units that can fetch an instruction and can decide when to issue each of the instructions. And also we have more specialized units. We have this special function, so-called special function units, that are some functional units for specialized operations like cosine or sine, and also specific units for load and store operations. So you remember last lecture and 2 lectures ago, Professor Mutlu talked about vector processors, array processors, and we saw like in the array processor we have several processing elements that can execute different operations, and we also have like the vector processor where we have different processing elements that are specialized. So this is more or less what we have here. You see, we have some specialized units like these ones here, and then we also have some more general units that these guys here that can, for example, execute a multiplication or an addition or a subtraction on integer or on floating point. Well, this entire thing is called a streaming multiprocessor, as I said in NVIDIA terminology, and as we mentioned before, in each of these streaming multiprocessors, we are going to launch at least 1 thread block, and usually not only 1 thread block. We can launch 2, 3, 4. That will depend on our program. Obviously, there is a limit. I cannot launch 300 blocks in this. Not me. I mean, the thread scheduler will not schedule 300 thread blocks in these streaming multiprocessors because the amount of resources, as we will see soon, is limited. But yeah, but I think the limit in current architectures is 32, if I remember correctly. But throughout this introduction to the programming model, we have talked about grids, blocks, and threads. And where are the warps? Well, the warp is a hardware concept. The warp actually belongs to the execution model. So the way the threads in the thread block are going to be executed on this hardware is by dividing the blocks into warps. And these warps have always 32 threads. The size of the block is something that the programmer can decide. For example, 64, for example, 512. The hardware will decompose this thread block that has been defined by the programmer into warps. And now we will start using this fine-grained multi-threading of warp, in which the warp scheduler will start issuing instructions for these warps in a multi-threaded manner, in an interleaved manner. So just to recall everything, streaming multiprocessors, compute units is the name in AMD architectures. These are our SIMD pipelines. The streaming processor CUDA cores are the vector lanes. And well, you can see here like how these 2 numbers have changed across the generations. Let's have our break, 15 minutes. And after that, we will continue with the performance considerations. Okay, let's continue. We have 45 minutes, and we should try to cover all the slides for you to have like a complete overview of what GPU programming is about. Even though we don't have time to go very much in detail through all the programming model and through other ways of optimizing the code for the GPU, but still it's good that we try to discuss as much as possible. So that's why this second part is called performance considerations. As I mentioned in the beginning, there are still two main bottlenecks in the GPUs. One are the access to global memory, the bandwidth to the DRAM, and the other one are the data transfers that are unavoidable between the CPU memory and the GPU memory. In order to optimize the memory access as much as possible, the GPUs have this latency hiding mechanism. This, you remember yesterday we mentioned that they are fine-grained multi-threading, and with this interleaving of warps, it is possible to hide the long latency operations. When you have a cache miss, you have to go to the global memory and read something from global memory, and this is a long latency operation that maybe takes hundreds of cycles, much like maybe 2 orders of magnitude more than a simple addition in the CMD pipeline. So, but the good thing is that while some warps are accessing memory, some other warps can keep executing arithmetic operations. So that's the latency hiding mechanism. Also, the way we access memory, we will have to try to have coalesced memory accesses. We will define them. And also because there are many times where we reuse data, where we have like different threads accessing the same data elements, it will be important to learn how to use the shared memory, because something that is going to be used very frequently by many different threads, is good to bring it from the global memory to the shared memory that is closer, so it is much faster for the GPUs to access. We will talk also about how to avoid the divergence, the branch divergence that we explained yesterday using, like, let's say, smart programming. We will give an example. And if we have time, we will also talk about atomic operations, the use of atomic operations, and how we can optimize their use, at least in one specific example. And finally, how to deal with the data transfers between CPU and GPU. We will say that in some particular cases where we perform computation that is independent on different parts of the input, it is possible to transfer some part of the input, start the computation on it, and then transfer the next part of the input, so that we overlap the computation of the first part with the data transfer of the second part. Okay, let's start with the memory access. And as I said, latency hiding, because these are fine-grained multi-threading machines. Yeah, you can see like a very toy example of what I explained before, right? If, let's say, you have 4 active warps, warp 0, 1, 2, 3, and they are, or the hardware is issuing instructions for these, like instruction 3 for warp 0, instruction 2 for 1 warp, and so on. And then it turns out that instruction 4 is a long latency operation, for example, a memory access, right? So the good thing is that while this long latency operation is executing, we can keep launching if the number of active warps that we have is enough, is large enough. In this other example, we only have 2 active warps, so you see that there is one gap here that there is one gap here that we cannot fill. So obviously, this will affect our performance. The ratio of active warps to the maximum possible number of warps is what is called the occupancy, and we will calculate the occupancy in each of these streaming multiprocessors, in each of these CMD cores, because actually they all these are like twins. They work the same. They're going to run typically the same number of thread blocks, and they have the same resources. It's enough if we calculate the occupancy for one specific of these SMs or CMD cores. And in order to calculate this, we need to take into account what's the maximum available resources. There are different limitations, because I mean the hardware is not infinite, right? So remember that each warp has its own program counter, and So we obviously need some registers that are the program counters for the maximum number of warps that we can execute in each of these SMs. Well, in current architectures, this maximum number of warps is 64. But there is also a limitation on the maximum number of blocks is 32. And then we have a certain number of registers. Recall this register, so this partition register file that is 256 kilobyte and a certain amount of shared memory that in current architectures is 64 kilobyte. So as you can see, a very simple calculation. If we want to launch thread blocks on my GPU that need to make use of 32 kilobytes of shared memory, what's the maximum number of thread blocks that we can have in each SM? It will be 2, right? But observe that the number of warps in each of these thread blocks is something that the compiler can define, because the number of threads per thread block is defined by the programmer in the execution configuration. The shared memory is also defined by the programmer, and the number of registers, it's also related to the programmer's work. If the programmer is more skilled, probably it will be, he or she will be able to write some code that uses less registers, but it's something that at least we can know in compile time. So with these 3 variables, we should be able to calculate what's the maximum occupancy, keeping in mind what are the available resources in each of the SMs. So yeah, that's a very simple calculation that will allow us to be conscious of what's the occupancy and what are the latency hiding possibilities that we can have in our kernel. So the second important thing regarding the memory access is the memory coalescing. When we access memory from the GPU threads, we want to make sure that concurrent threads access nearby memory locations. That's what we call memory coalescing. And as you can see here, peak memory bandwidth utilization occurs when all threads in a warp access one cache line. One cache line typically is 128 bytes in these architectures. So if I have these 32 threads accessing bytes or words that are in these 128 bytes, I will get the maximum possible bandwidth. And so how should we do that? Well, not this way. This is a matrix MD, and we want to access this matrix MD. Let's say we are starting to program CUDA, we are not very skilled, and we decide that, well, with this matrix we need to do some computation, and this computation requires threads to be assigned to several elements of the matrix. So what we could do, for example, is say, okay, let's assign this thread 1 to this row, and this thread 2 to this row. So what's the problem here? The problem is that it's going to be, these two probably will belong to the same warp. So if they belong to the same warp, they are executed at the same time. And if they have to access memory, because they need to get data elements from this matrix MD, they will access memory at the same time. And now observe that if the first memory access of thread 1 is here, and for thread 2 is here, there is a stride, right, between these two memory locations, and this stride is equal to width. If my matrix is very small, okay, the stride is not a problem, and they might be even still be in the same cache line, but if the width is 4K, then for sure they will go to different cache lines. And the problem here is that for these two threads, I will actually need 2 memory accesses. So I'm reducing the maximum possible bandwidth by 2. What's the smart way of doing these things? So what we will do is assigning the threads to the columns in a way that thread 1 reads here, thread 2 reads here, and the stride is just 1 or maybe 2 or something. But this way we can have a much more efficient memory access. Here you can see the same story, but probably in a more clear way. This is a matrix. You know that your matrix is stored in a row major layout. If our access direction for each of the threads is like this, we assign the rows to the threads, what will happen is that first thread 1 in the first memory access reads here, thread 2 reads here, and if these two are too far from each other, they will be in different cache lines. So in the end, for this particular example, we will need 4 memory access for this first time period, and then the next time period, another 4 memory accesses. In a coalesced memory access, we access this way, so these 4 memory requests here can be coalesced. We can access the 4 elements at the same time, and we will achieve peak bandwidth. This is related to the way we organize data. Remember actually that yesterday when I explained the matrix multiplication example, I said, oh yes, accessing matrix B might be a problem because these two are, there's a stride, the stride was 10, and I mentioned, okay, at some point it would be possible, or it would be good to transpose the matrix so that instead of accessing rows, so columns of matrix B, we access rows of matrix B transpose, right? So this is actually something that it's quite useful, especially when we have heterogeneous systems in which CPUs and GPUs, different devices that might have different preferences in the memory access need to share some data structures. And here is where it comes the distinction between an array of structures and a structure of arrays. For example, let's say that this is our data structure. One possibility of organizing these data elements is having something like this, where, for example, for this array A, we have all the blue elements in a row, and then we have all the green elements and all the white, the yellow elements. This is a structure of arrays because each of these can be considered an array. And here we have an array of structures. Each of these with 4 elements is an struct, and with a float A, B, C, and an integer D. And the interesting thing here, also if you observe these 2 graphs, is that CPUs and GPUs have different preferences. So for the GPU, because of the fact that you have many threads running in parallel, and these threads usually are going to execute exactly the same operation at the same time. So we have thread 0 in let's say 1 warp, right, where we have 32 threads. We have thread 0, 1, 2, 3, 4, and typically what we're going to do is that we are going to assign each of these threads to consecutive elements in our array. So thread 0 will read this, thread 1 this, thread 2 this, thread 4, and so on. So they are all in the same cache line. We are reading them all at the same time. If we do something like this for a GPU, in the first load, thread 0 is here, thread 1 is here, thread 2 is here. There's a stride, so we might need more than 1 memory access, right, for each of the warps. But it turns out that in CPUs, an organization like this is good because the CPU is probably 1 single thread. And if it's just one single thread, when the CPU reads this element, all these elements here that probably will belong to the same cache line will be retrieved from the memory and stored in the cache that is closer to the CPU core. So as you can see, for these graphs, this is a throughput, so higher is better. And on the x-axis, what you have is a stride, the structure size. You can think about something similar to the structure, the 2 organizations that we have in the previous slide. And when this stride increases for the GPU, the throughput goes down dramatically. But on the other hand, for the CPU, it tends to be the other way around. So you can see that for a bigger struct, the CPU tends to have like a higher throughput. Okay, so this was related to the way we should try to access memory. Now, as I said before, sometimes there will be some memory locations that are shared by neck boring threads. So this is a very simple example, also related to image processing. This is the main loop in a Gaussian filtering. We have our image here, and this is like a Gaussian filter. The Gaussian filter is typically some kind of mask that we put on top of the image, on top of these different pixels of the image. And what we do is, as you can read here, but maybe it's even easier to understand if you look at the image. For this specific pixel, what the thread that is assigned to this specific pixel is going to do is going through all these 9 elements that you see in this green window here. So it will compute the multiplication of the specific pixel times the specific value of the Gaussian mask, and will accumulate the result. And observe that if I have, let's say, thread 0 here and thread 1 here, thread 1 will have to access all these 9 elements here. So it turns out that they are sharing 6 of these elements, right? So it seems that it doesn't make any sense to, let's say, go to memory to get this element for thread 0, and then go again to memory, to the global memory, remember this latency of hundreds of cycles, again to get this element for thread 1. So what we will do in these cases is what I called before tiling. We're going to divide the image into tiles, and what we will do is loading these tiles into the shared memory. Recall that the shared memory is in the streaming processor, in the streaming multiprocessor, in the CMD pipeline. So it's on chip, so it is much faster. So for example, if we are using thread blocks of 4 times 4 threads, what we will do is loading all these tiles here, because all these are the image pixels that are going to be accessed by the 4 threads calculating the result of the Gaussian filtering for these pixels here. And yeah, maybe this one, for example, is only going to be used by the thread working here, or this one is going to be used only by the thread working here. But all these 8 pixels that we have in the middle are going to be shared. So the code in the previous slide will be transformed in something like this. We need to declare in our kernel, and this is, I mean, you can, I mean, this is already CUDA code, right? So we have to declare this L data, local data array in shared memory. We will have to tell our threads, go to global memory, read this, and load into shared memory. And then at that point, we will synchronize to make sure, because, you know, here we are only using like 4 threads, and 4 threads is a very small number, but now consider that our tile or thread block, instead of being 2 times 2, is 32 times 32. If it's 32 times 32, 1024 threads, we have 32 warps there, right? So these warps, as you know, are scheduled independently on the CMD pipeline. So at some point, we want to make sure that all the 32 warps finished loading the corresponding part into the shared memory. And that's why we need to use this local barrier, this sync thread. And right after that, we have the loop where the threads will be accessing L data from shared memory, so the performance will be much faster. So this is the shared memory. It's very useful. I mean, it requires a little bit more knowledge in order to use it in a smart way, because this shared memory is a banked memory. Recall yesterday's lecture, we have the CMD pipeline, or we have the vector, and if we want to get full bandwidth from memory, it's good that the memory is banked. So that's more or less what we have here. Typically, this shared memory has 32 banks, and this is good for the warp, for the size of the warp. As you know, the CMD pipeline will issue the load or the store operation for the entire warp at the same time. So the size of the warp is 32. So if these 32 threads have to go to the 32 banks, well, we will get maximum bandwidth if each of these threads go to a different bank, right? But otherwise, we will have a problem. We will have a bank conflict. Yeah, so let's, I mean, you're already familiar with this, but let's take a very brief look at this. We have our threads on the left, we have the banks on the right. If the stride is 1, we have a linear addressing, like, let's say, array A TID or thread ID.x, we will be accessing something like this. So there is no bank conflict here. Maybe the addressing is different, maybe even random, but provided that each of the threads go to a different bank, still we will get a maximum bandwidth from this memory access. When are we going to have bank conflicts? When we have, for example, in this case, 2 threads accessing the same bank, probably different memory positions, okay? It doesn't need to be the same memory address. And actually, if it's the same memory address, that's good, because we just need to access once, and then the retrieve value is broadcast or multicasted to all the different threads that want to access the same value. But the problem is when it's not the same address, it's different addresses in the same bank. Then is when we will see the, in this case, 2-way bank conflict, or here we have an 8-way bank conflict. And well, there might be ways of reducing the bank conflicts, and we already talked about something yesterday. We mentioned the possibility of changing the layout, like the transposition, and we also talk about the possibility of having kind of randomized mapping. You recall this paper by Bob Rowe. But there is another way, even easier. It's very simple to be used by the programmer, and we don't need to rely on very, let's say, specific hardware solutions. I'm going to give you a very quick example of this. Yes. Okay. Yeah, let's, this is padding in shared memory. Maybe we have some CUDA code, kernel, where, I don't know, we will load some data into the shared memory. Somewhere here, we declare the shared, let's call it L array with certain size. And we load data from global memory into the shared memory, into this local array. We'll have to sync threads. And after that, our threads have to access the values that we have stored here in the L array. And maybe the element that each of the threads is going to access is 2 times thread idx.x. Okay, so you see that the stride between 2 consecutive threads is going to be 2. And after that, computation continues. So what's the problem here? The problem is that we're going to have bank conflicts. Let's consider, instead of considering warps of 32 threads and 32 shared memory banks, let's consider 8 for this toy example. This is our shared memory. And these are the different shared memory positions. This is bank 0, 1, 2, 3, 4, 5, 6, and 7. So each of these columns is one bank. And if I want to access this way, I will have thread 0 reading this element, thread 1 this, thread 2 this, thread 3, and then here, thread 4, 5, etc. So what's the problem? As you can see, we have two threads that belong to the same warp accessing the same bank. So this is a bank conflict. Bank conflict. A very easy way of solving this using padding. Again, we have the 8 banks here. And now what we are going to do is that every 8 elements, we are going to pad. Pad means that we are going to keep this memory position unused. So we won't store anything here. The value that is here in this original mapping will be stored here. And the value that is here will be stored here. So we pad every 8 positions, every 32 on a real GPU these days. And this way we will have thread 0 here, 1, 2, 3, and thread 4 here. So observe that now these 2 threads are accessing different banks, no bank conflict. Right? As you can see, it's a very simple software solution to deal with the shared memory bank conflicts. It's very useful, especially when we have these regular strides. Okay, yeah, and finally, there are like other solutions that can be even be ad hoc for each specific application. Like, for example, the use of hash functions. You might want to take a look at that paper if you are interested. Okay, now let's continue with the SIMD utilization. Recall yesterday we talked about branch divergence, and then we say, okay, it will be possible to have some kind of dynamic warp formation that will reduce the branch divergence and will increase, not actually reduce the branch divergence, but will increase automatically the SIMD utilization. Well, that, as I explained, was a research proposal, but there are some ways of dealing with this from the point of view of the programmer. Let's have a very simple example here, something like this code, in which you can see in this code, like even threads are going to do this, odd threads are going to do that, and if on the picture on the right you see that there are many threads, let's consider that we have 64 threads, so these are 2 warps, right? So what we will have is that half of the threads will go through the if, the other half will go through the else. And obviously the problem here is, recall how this was executed using the mask, as we explained yesterday. The problem is that for this if, I will have all the threads from warp 0, and then all the threads from warp 1, from warp 1, and then for the else exactly the same. So in the end, in order to go 2 warps going through these 2 parts, if and else, we will need like 4 passes, right? Because in the if, only half of the threads are active. In the else, the other half of the threads of the warp are active. So it might be, in some cases, easy and not so difficult to change the way we assign the threads to the computation. And for example, instead of assigning even threads to do this and odd threads to do that, what we could do is something like this. We could tell threads with an index lower than 32 would do this. Those between 32 and 63 will do that. So this way, in the if, all the threads that are working belong to the same warp. In the else, all the threads that are working belong to the same warp. And here you can see an example. Vector reduction. What's the vector reduction? Is you have an input vector, and what you want to compute is the, for example, the maximum or the minimum of all these elements, or for example, the the total addition of all these elements. So one way we could do it in a naive mapping would be something like this. We could say, okay, let's use only even threads in a way that in the first iteration we have thread 0 computing 0 plus 1, thread 2 computing 2 plus 3, and so on. And in the next iteration, half of the threads retire, only half of the threads remain executing second iteration. Thread 0 will compute 0 plus 1 plus 2 plus 3, and so on. The problem here is that these threads are consecutive, so they belong to the same warp, right? And if they belong to the same warp, what we do here, what we have here is that the SIMD utilization is 50% in the best case, in the first iteration is 50%. So yeah, here you can see the code. It's more or less, I mean, you can take a look by yourself, but the key point, the key is here, where you can see that this modulo operation makes only, in the very first iteration where it's tried this one, only even threads go to the this partial addition, and yeah, half of the threads retires every single iteration. In a divergence-free mapping, and actually this is possible to do because in these kind of operations that are associative, right? It doesn't matter what's the order in which I add the element. So we could do something like this. We could have like a bunch of compacted threads, thread in this case 0 to 15, computing the partial sums. For example, thread 0 adds element 0 and element 16, thread 1 adds element 1 and element 17, and so on. The number of iterations is exactly the same, but the good thing here is that now all the threads that are working, it is much more likely that they belong to the same warp. And even though in the last iterations, we will keep retiring threads, and because actually in the last iteration, as you know, only one single thread will work. But if the total addition that we are doing is maybe an addition of 2048 elements or 1024 elements or something even bigger, in most of the iterations, we have 100% utilization in each of the warps. So you can take a closer look by yourself at this. We continue with atomic operations. I'm going to go very, very quickly here. So atomic operations are needed when threads might need to update the same memory locations at the same time. Because we have many concurrent threads. They are executing, yeah, many, more or less, the same program and probably the same instruction most of the time, right? So there will be many times in which, for example, we read some element, we update this element that we have just read from memory, and then we store the result back to memory. If two threads that are executing at the same time because they belong to the same warp need to update the same element, the problem is that they will read the same value at the same time, they will update, and they will write the result of the corresponding update. And probably this will produce a race condition, so the result won't be correct. You can see this is some syntax. You can take a look at yourself. This is CUDA code, this is PTX, this kind of intermediate representation, and here what you can see is like the assembly for different architectures. But it's quite easy to see here. What's the problem of having these atomic conflicts is that if you don't have atomic conflicts, you will have both threads updating some, in this case, shared memory positions at the same time. This will be your total latency for this operation. If these two want to update the same element, element 2, then you have an extra latency because of the conflict, right? So the atomic conflicts serialize the updates. And this is like a very good example, histogram calculation. I guess that you all know what a histogram is. You have the definition there and the code of the pseudo code for a sequential computation of histogram. But if we want to do this in GPU, and we can do it, right? Because We typically calculate histograms for images, and images have many pixels, so ideally we should be able to use many threads at the same time. What we would do is assigning the threads to different pixels, and these threads will read the image, and depending on what's the value of the image pixel, they will update one particular position in the histogram. And obviously we want that, for example, these two, thread 0 and thread 2, because they want to update bin 1, we want them to both read, add 1 and write, and then the other one read the partial result, add 1 and write. So we want the total value be 2 instead of 1. So we need to use atomic addition in this case. The problem is that when we compute, for example, histograms for natural images, it's going to be very frequent that we have this kind of atomic conflicts. For example, here you see the forehead of the lady, and these are the values of the pixels. We have these two pixels that are neighbors, and they both have the value 192. So these threads assigned to these pixels will go and try to both to update the same position, 192 in the histogram. Ways of solving this using privatization. So what we can do is like having partial subhistograms, assign each of these subhistograms to different blocks, and when these blocks go through the entire image and calculate the partial subhistograms, they merge the partial results into a final histogram in global memory. Yeah, so we are improving the performance here because we reduce the latency of this shared memory access. I mean, the shared memory is closer than the global memory, so if we perform the atomic operations on the shared memory, that will be faster than going through to the global memory, and also because we are reducing the amount of conflicts. We have a smaller number of threads wanting to update the same histogram bins. And the last part, just for you to take a closer look, as I mentioned when we started talking about these performance considerations, there might be some cases in which the computation that we need to execute on the GPU, it's, let's say, chunk-wise, or it's part of the input-wise, right? So you see that you already know that we need to move data, input data from the CPU memory to the GPU memory. This is this green bar, this copy data that you see there. And when all the data is in the global memory of the GPU, then we start the computation. That's the red part, right? But if we are, I don't know, like transferring 1,000 images, and the computation that we need to execute on these images is independent. I mean, I can operate on image 0, and another guy can operate on image 1, and the computation that we do is independent. One thing what we could do using these asynchronous transfers that exist in CUDA and also in OpenCL is something like this. We could divide the input into different chunks. We transfer the first chunk, we start the computation for the first chunk, and at the same time we transfer the second chunk, and so in a way that we overlap. So as you can see, we save some time, and I mean, you can take a look by yourself at these simple equations that give us an estimate of what's the final execution time that we will obtain. Applications to this, you can find applications to this, for example, in video processing. Video processing, typically we operate on the different frames of the video independently, or maybe we need to use several consecutive frames, but usually this happens in a window, right? I mean, a certain number of frames. You don't need to have the entire video. So yeah, probably a simple solution can be something like this. We could transfer the entire video. In this case, it's like a very toy example with just 6 frames. We could transfer the 6 frames and then start the computation. This is like the naive approach. Or we could divide this video into smaller chunks, 2 frames each. In this case, we transfer these 2 frames, and while we are computing, we have threads working with these 2 frames, we transfer the next 2 frames. And in the end, we save all this execution time here. So this is the end of the presentation. This is the summary, the different things that we have covered. If you have questions, please let me know. If you are interested in GPU programming, I mean, for sure you will have a chance to learn parallel programming here in your bachelor degree. And but anyway, I'm always open to talk about that with you and maybe give you some orientation or some advice. But if you also want to have fun, maybe you can take a look at this course in Barcelona in July that will be taught by probably the best teacher in this, the best professor for these matters in the world, who is Professor Wenmei Hu. You already know him. This is the PAMS, and actually this year is also focused on artificial intelligence and deep neural networks. So yeah, you can take a look at this, maybe not for this year, maybe for later editions. Do you have any questions? No? So thank you very much. Enjoy the weekend.